If you were like me at first, you would be horrified by the Riemann sum definition of the definite integral. All right? But now I have thought differently and I have been purified of my sins and I understand now how genius this definition really is. And that's what the point of today's video is. We're going to use the definition of the definite integral with the Riemann sums to prove many properties of the definite integral that we know and love. But first, let's review what a Riemann sum is and what a definite integral is. A definite integral, for the purposes of this video, is just the area under the curve of a function, and it's just a number, okay? And this is the exact area of a function's curve, all right? This value here. But the right-hand side is showing an approximation of this area by using rectangles. So how do we do that? You divide your interval from a to b into n subintervals, and each of them has its own rectangle associated with it, with a height of the function evaluated at some point x within the subinterval. That's what xk here means. And so the height is f of xk. So you can pick a point like this in the middle of the interval to make a rectangle for the subinterval. And the thickness of each of these rectangles is known as delta x at the kth subinterval. And the best part about this is that when you have uniform step sizes and uniform subdivisions of your intervals, then it's just equal to the average. It's the b minus a over n. So that's what we have here. And for the purposes of this video, we're going to be using the b minus a over n version of the Riemann sum definition of the definite integral to prove certain properties. All right. And again, this idea of increasing the number of rectangles within a certain finite space means that those rectangles are going to get smaller and smaller, which means that they will approximate the area better and better. What that essentially is shown as is over here in the bottom expression as the number of subintervals you have going to infinity. All right, as the number of rectangles you have, which is n, as that goes to infinity, each of the rectangles will be smaller, and that's reflected in the top definition. And what max delta x right here is called the mesh size. It's the largest possible rectangle that you have. Because again, you can define the subspaces to be as big or as small as you want. And as long as the largest rectangle you have eventually goes to 0 in the long run, as you put more and more rectangles in, then so should all the smaller ones. Okay, that's the review out of the way. Now let's go and look at some of the properties that we know and love. First of all, we have linearity. These are the first two properties here. What this says is that the integral of f plus or minus g dx is equal to the integral of f plus or minus the integral of g. In English, the integral of the sum or difference is the sum or difference of the integrals. And the second part with constants. The integral of a constant times a function is the constant times the integral of the function. You can hop it out. Okay? And that's the first thing we're going to prove. All right? The next thing we're going to prove after that is the reversal of direction. Okay? The integral from a to b of f dx is minus the integral from b to a. So reversing the bounds of integration actually gives you a negative sign in front. And while this doesn't seem to make much sense practically, this is actually super important in things like physics when you're computing the values of force and work, okay, and their directions, if you're talking about forces, okay? Then we're going to show the no area definite integral property, that is the integral from a to a of f of x dx equals 0. Intuitively, this makes sense because, of course, the integral from a to a is just one strip. It's a line, and lines have no area, okay? And again, by convention, we integrate from left to right, so the reversal of direction, it might make sense to say negative if we're thinking about reversing the direction of integration from right to left. And finally, what I call succession or transitivity, the integral from a to c of f plus the integral from c to b of f together is the integral from a to b. And this makes sense because if we put down a c somewhere in between a and b, then it makes sense that the area of this function from a to c added to the area from c to b should give us the total area from a to b and cut out the middleman. So these are all properties that are being used after we prove them in the proof of the fundamental theorem of calculus, which is why you cannot jump to it right away if you want to be rigorous. Okay, without further ado, let's get into it. And just for the sake of speed and time, and I'm a little lazy, when I write limit, I'm not going to be writing limit as n goes to infinity or limit as max delta x goes to 0. Instead, I'm going to write L, if that's okay with you guys, because it takes a while. Everything else I'll write out, and we're going to use the bottom definition, don't forget, this idea of the b minus a over n, because it's going to be a bit easier. Okay, so let's get into linearity. We want to show that the integral from a to b of f plus or minus g of x, all right, and when I write f plus or minus g without any variables, it's assumed that they're in the variable x, dx, should equal the integral of a or b, from a to b, I mean, f dx, plus or minus the integral from a to b of g of x dx. So let's show this by starting with the right-hand side. By definition, what the right-hand side is a limit, okay? And this is the limit as n goes to infinity of the sum, n or k going from 1 to n, of f of xk plus or minus g of xk. This is a one function, okay, in the integrand. So you have f of xk plus or minus g of xk. And you can think of this even more rigorously as defining a function h of x to be the sum or difference of these two functions and then split it later, all right, times b minus a over n, like this. Now, of course, within the sigma, you can distribute this b minus a over n term and you get limit, okay, of the sum as n goes, as k goes from 1 to n, of f of xk times b minus a over n, which I'm just going to write as delta x, if that's okay with you guys, plus or minus g of xk, delta x. Okay? And what a sum is, the sigma, is really just a summation. You're just adding a bunch of terms together. And if you're adding terms that are themselves added, it doesn't make a difference. You can split the sigma into two. And what I mean by that is you can literally just take this term, move it off to the side, and split the sum like this. And don't forget that the limit applies to the entire expression. But then, by the arithmetic of limits, and if you don't know how the limit properties are working or how they're proved, please do check out my epsilon delta mini-series that I have on this channel. But essentially, we have a sum or difference here, and the limits themselves are linear. The limit of the sum or difference is the sum or difference of the limits. So this allows us to put a limit in front of both of these expressions independently of each other, like this. And now, by definition, you can see that this expression is the integral from a to b of f dx, plus or minus, by definition, this expression here is the integral from a to b of g dx. And there you go. There's a rigorous proof of this idea of linearity with sums and differences of functions. And this also can expand to f plus or minus g plus or minus h plus or minus j of x, all these different functions together. So you can compound this together. It just means distributing the delta x term over the sigma. Okay. The next property we want to prove was the integral from a to b of cf dx, okay? And remember, if I write cf without an input variable, you're assuming that this f is a function of x. That's equal to c times the integral from a to b of f dx. That's what we want to show, so we can't actually set them equal just yet. Okay, now, with the left-hand side, by definition, this is limit of the sum, k going from 1 to n, of c times f of xk, delta x. And you're going to notice I'm not going to write b minus a over n because we actually don't need it for this proof. And of course, using the idea that the sigma, all right, the sum is linear, then what's happening here is you're basically adding a bunch of different sampled values of f of xk for different k, but they all have the same constant c. So taking it out is the same thing as factoring it out. So we are allowed to do that with a sum. And so we can move the constant out or onto the outside. And then because you can do the same thing with limits, all right, don't forget that the limit of a constant times a function is equal to the constant times the limit of that function. And once again, go back to my epsilon delta mini-series if you want to have a proof or explanation of that. So we can hop the constant out yet again, like this. All right, and now look, this expression here is just a plain old integral that we know and love. C times the integral from a to b of f dx. That's not so bad, is it? And all thanks to Riemann sums. But hold on, we're not even done yet. That's linearity there. Now, let's prove the change of direction property right here. The integral from a to b of f dx is the minus integral from b to a. And this is where we're going to want to use our idea of b minus a over n. So, let's start with the integral from a to b of f dx. By definition, of course, this is the limit of the sum, k going from 1 to n, of f of xk times b minus a over n, like this. b minus a over n. But remember from regular algebra that c minus d is the same thing as minus quantity d minus c. You're basically just taking the minus 1 out. And that's exactly what we're going to do here. We get, if we take the minus 1 out of here, what do we get? We get, instead of this, we get times minus a minus b over n, correct? So you have a minus b. And now we're basically just doing a constant linearity idea here. We're taking this constant of minus 1, and we're hopping it out of the sum, and by the property of limits, we can hop it out of the limit. So we're left with minus the limit of the sum, k going from 1 to n, of f of xk times delta x, which in this case is a minus b over n. Which by definition, looking at the definite integral, means we get minus integral from b to a this time, because now b is second space here, like this. So that's really cool, and that did not take much work at all to prove. And so that's interesting that many classes don't actually show you how to prove these basic definite integral properties, and they don't give Riemann sums enough justice and love. Okay, so that's that proof done. Now let's go and move on to the zero area principle. All right, this is the same thing as writing it out as integral from a to a f dx. By definition, what is that? Well, it's the limit, of course, of the sum, k going from 1 to n, of f of xk, and what's delta x here? It's b minus a over n, but in this case, b is a. So you get a minus a over n. And of course, that means that a minus a is 0. So this whole term goes to 0. And because it's multiplied by the f of x, this entire thing goes to 0. And what's the same thing as adding a bunch of zeros together? It's 0. And what's multiplying, or what's applying a limit to a constant function of 0? It's 0. And so you can see that the integral from a to a of f dx is 0. And that's the rigorous explanation, even though you wouldn't really need one. So there you go. That's probably the easiest proof that we've got here. And of course, now it's time for the last proof, my personally favorite one to do. It's the succession. So we want to show that the integral from a to c of f plus the integral from c to b of f is the integral from a to b. So let me just move that down here so we can have it in view. All right, perfect. So let's start with the left-hand side. By definition, we can write this as two different limits, okay? And these are limits as n goes to infinity, okay? So you have limit of the sum, k going from 1 to n, of f of xk times b minus a over n, but in this case you have c minus a over n, right? So c minus a over n. And then the other limit here, or the other definite integral, is written as the limit of the sum. I'm just going to copy it because everything here is the same except the delta x term, okay? In this case we have b minus c over n. So I'm just going to write that down real quick. So here you have b in blue minus c in green over n. And now, remember, last time we used the limit of the sum as the sum of the limits. Now, we have the sum of the limits should equal the limit of the sum. So you can bring these two expressions together under one unified limit, like this. Okay? And now, notice, we have things being added together with the same k and to n bounds. So we can basically combine these two sigmas together as well. So you can get rid of it like this. And once again, if you're confused how that works, you're basically just adding a bunch of terms together. And in English, it's going to sound weird, but the sum of the sums is the sum of the sums. So you can basically do what's called inverting splitting the sigmas. So in the last proofs, we split one sigma into two. Now we're doing the opposite. Okay, and now notice that you have f of x times c minus a over n plus f of x times b minus c over n. Guess what we're going to do? We're going to factor out f of xk. And when we do that, what do we get? We can get rid of the f of xk here at this point. And look, we have c minus a over n plus b minus c over n. They're over the same variable n, so we can bring them together under the same variable n, like this. All right? And what do we do now? Well, c minus a plus b minus c is what? Well, these c's cancel, and then you have b as a positive minus a. So I'm going to rewrite this like this. We have L times the limit times the sum, k going from 1 to n, of f of xk times, now we get b minus a over n. And there you go. We have that classic definition of the definite integral with a uniform step size, delta x. And so therefore, we can say that's equal to the integral from a to b of f dx. And so we cut out the middle band c in this proof and in this expression. and we've proven the rule of succession. Okay? And there you have it, folks. That was 5 integral properties that are very elementary, very basic to know. And most classes in math don't go over how to actually show them. They show some intuition for them, but if you want real rigor, which is what a lot of calculus is based on, you won't get it. So I hope that this was helpful in explaining just how important Riemann sums are to the definition of the integral and how useful they are. And in fact, you'll see that you're going to use these properties of integrals in even more advanced ways in multivariable calculus too. And remember, it all stems from the properties of limits and the properties of summations, including factoring, constants, and other variables inside. So I hope you enjoyed the video. See you in the next one.